Alright everybody, this is a video on derivatives. So the basic question of what are derivatives. If you're in calculus now or you've done calculus in the past, you're either getting exposed to them or you've been exposed to them, and there's a good chance that you're just going to memorize certain rules in calculating derivatives, but you're probably not going to understand what those rules actually mean or even how to apply derivatives in real life. So the point of this video is actually going to try to give you a basic understanding of what's underlying these kind of rules that you use in derivatives. It's going to touch only on the basic aspect of that, but it should open up the door when it comes to understanding these things. So just to start, we're going to talk about slope. Slope is basically what a derivative is. What slope is telling you is how fast something is changing. For every input that you put in, which is your x value, how much does the output change, which is your y value? So the basic formula of y equals mx plus b, any line, straight line is basically described by this formula. M is the slope. In explaining this slope, you are essentially saying, okay, for every value x that I put in, I'm going to multiply that by the slope, and that will give me my output. This plus b value is kind of your starting point. It's called the y-intercept. We can, in many cases, consider it to be 0, but just to give you an example, I'll give you speed of driving over time, so miles per hour or kilometers per hour if you're not in the US. And we're going to start with the idea that we're starting at a distance of 0. We're going to try to figure out how far we've driven in a number of hours. So let's say we're doing 60 miles an hour, and I want to know how far we've driven in 1 hour. So our input value for x would be 1 hour. Our slope would be 60 miles per hour. And our starting point, we'd start at 0, so our b would be 0. So what that's telling you is you'd multiply 60 miles per hour times 1 hour. Since you're starting at 0, you add 0 to that. That's 60 miles in 1 hour. For the second hour, you would just designate 2 for your x value, and you would get 60 miles per hour times 2 equals 120. You'd have traveled 120 miles an hour. The starting point could differ. So let's say you start measuring your distance after already traveling 10 miles. Well, then in that case, b would equal 10. And you would say 60 miles an hour times the first hour would be 60 miles. I've traveled 60 miles in the first hour, but I've already traveled 10, so that's 60 plus 10 is 70 miles. So hopefully that gives you a good idea. This is what that would look like. So not necessarily a slope of 60, which was what slope we had previously, but we have a slope of 1 in this case. Y equals 1x, 1 is our slope, x is our input, plus 0. B is equal to 0 in this case. That can easily be simplified because any value is inherently multiplied by 1, so we can get rid of that 1, and 0 is just 0, so we can get rid of the 0, and that just becomes y equals x. What that means is for every input x, you just take that, and that's your output. So here on the graph here, you put in 2, you output 2. You put in 4, you output 4. Any number you put in, you output that same number. That is just an idea of a very, very, very basic line. It can change in slope, it can change in y-intercept, but it will look something like this. That's all well and good, but in real life, things are not perfect lines. So what happens when things get a bit more curvy? So that basic formula for slope, it no longer really works. Now your slope kind of lies to you. So in order to fix this, you got to get a little creative. To start though, before we add the creativity, let's look at the starting point. In calculating your slope, so in calculating this m value, all it is saying, if you've ever heard the term rise over run, you're calculating the difference in the y values and you're dividing that difference by the x values. So this formula here says basically this is y1, so this is like your second point, and x1, this would be the x value of that same point, and you're taking the difference of the first y value, differencing the second y value, and the same for the x's. As an example, it's a little funky, so as an example, let's say we have 2 points, 1, 3. The x value is 1, the y value is 3, and 4, 5. What I'm going to do is input the y values into the numerator, so up here and up here, and I'm going to take that difference. It doesn't matter which direction I go, whether I put 5 or 3 first, but I have to associate the appropriate x in the same order on the denominator. So here I'm going to do 5 minus 3, that gives me 2. And I'm going to divide that by 4 minus 1. And again, the 4 is associated with the 5, so that comes first. And the 1 is associated with 3, they both come second. So my output would be 2 over 3. That is my slope. My slope for every 3 values I go over, which is this x part, I go up 2. Okay? So going back, that's the basic way to calculate it. But the reason that doesn't work here is because I have a changing slope. If I take 2 points, as I did here, these 2 points and this line that designates the slope doesn't really tell me what that slope is at that point. It's really actually inaccurate. If I look at the next one, I've moved the points a little bit closer to one another, and now I have a little bit more accurate of a slope. If I move them even closer, I have an even more accurate of a slope. So it starts getting more accurate the closer I put these points together. But the thing I need to do is get these infinitely close. I need to get them as close as I possibly can together. And then the question is, well, how the heck do I do that? So that's where dy dx comes in, or basically kind of the core of derivatives. You see this everywhere, dy dx. Well, this d just means delta. And if you're familiar with delta, delta just means change in. A lot of times they'll have delta being a triangle, and they'll use it for things like temperature, so change in temperature in Fahrenheit or Celsius. D just means change. So what this is saying is change in y over change in x. Well, what's fantastic about that is, let's go back. Well, this is change in y over change in x. So it's actually saying the same thing. It looks more complex. It's a little more confusing. You're not familiar with it, but it's the exact same thing. But the goal is to make this dx value tiny, and we're going to get into that. This is also kind of, in many ways, called limits. Maybe there's a difference between the two. As far as my applications have gone, limits and derivatives are basically the same thing. So we're going to talk briefly about limits, because when you get into that, you'll see these h values pop up. Might be something else, but usually it's an h. And what we do in this case is, instead of having 2 points, which would be, the x0 and y0 as their first point, and x1, y1 as your second point, you use just 1 point. But you modify that point by this tiny, 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 tiny value of h. And what that does to your formula, I'm going to lie first here, so bear with me. What that does to your formula is, now your difference in y, which is the top value, is actually the same point, y0 and y0. But this I'm gonna change slightly by adding in this h. So it's a sliver of a difference. Then on the denominator, you do the same thing, but you do it to the x. So you sliver of a difference of the point of the x minus the original. It doesn't quite look like this. And I show you this because you can associate this directly to that first calculation of slope. But what you do instead is you alternate the y for the f of x. The reason you do this, and I'll explain what f of x is because we're not actually adding the h to the output. We're adding the h to the input, and you're getting an associated change in output. So if I put in, 2 as my original, and then I put in 3, I don't just add 1 to the output as well. I have to add it to the input only, and then I calculate the output from that. So this is somewhat of a lie, but the idea, the form of it is about correct. So I'm going to exchange y for f of x. The reason I'm doing this is because y, which is my output, is a function of x. That means that there's a rule attached to the input of x and the output of y, and that rule is called a function. And what I can do with that is, instead of just putting x as my input, I can put x plus h as my input. And therefore the output is associated to that rule, to the input. So I have my newly adapted output minus the original, and I have my newly adapted input minus the original. What you'll notice is there's an x and there's a minus x, and those actually cancel out. So now you get almost an unfamiliar formula here. But all it's doing, again, is the change in y on top and a change in x on bottom. So you're doing the exact same thing that you did with slope, except you've added this little h here. So as I said, nothing changes, except that h now is tiny. It used to be a full digit or multiple digits, but here in this case it's fractions of a digit. And because it's almost the same, but it is a different number, it is incredibly useful. And we're going to move now from h to dx. These are essentially the same thing. What either one means is that you're taking an increment, a tiny, 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 tiny value in change. And it can be called h or dx depending on how you're applying it. And we're going to apply it to this example. So this is x squared. It's a parabola. And the question I'm asking is, how do you find the slope? No matter where you are on that parabola, that slope changes. If you're at 0, the slope is 0. If you move off of 0 to the right, it starts to increase slightly in value, and it starts to increase faster and faster and faster the further you go right. And it starts to decrease faster and faster and faster in value to the left. So there's no one slope to this formula. is what I'm getting at. So the answer to this is actually you have to solve it as a formula. In order to do that, in order to kind of understand how we're doing it, we're going to perceive this parabola as this. It is x squared. X squared is literally a square with sides of x value. The input will be the side. So the input is our x. The output is the area. So basically, if I have y equals x squared, for any number I put into x, the output, I'm just going to take that value and multiply it by itself. So if I put in 1, I have 1 here and I have 1 here, and the area would be 1. If I have 2 here and 2 here, the area would be 4. In this case, I have 9 here and 9 here. The area is 9 times 9, which is 81. So these are actually representing our points. So at any one of those points, in this case, it's 9 is our input, so our x value is 9, and 81 is our y. So the point is 9, 81. What if we not only have 9, 81, which you notice here is 9, 81, but we also have 10, 100. We've now incremented by a whole digit. So it's gone from 9 on the x value to 10 on the x value. The y value has gone from 81 to 100. So we want to know what is the slope from point where x equals 9 to x equals 10. We can calculate it like this. Plug it into the slope formula, find the changes in the y's, which are 181, and over the changes in the x, which are 10 and 9. And here you'll see 100 minus 81 over 10 minus 9. Well, that equals 19. Okay, all well and good. Or we can do this. You can literally count the boxes that are different between the two. If you notice, if I take out the red boxes, you have the same box left and right. If you count those up, it's 19. So wonderful. We found the slope 2 different ways, and we visualized it actually. But the catch is here. From 9 to 10 on that curved parabola, there is not a, at each decimal point, if you will, it's not the same slope. It's all around 19. In fact, 19 is the average between those two, but it's not 19. So you got to figure out what the actual slope is at the point of 9, which means you got to do not a difference between 9 and 10, but a difference between 9 and 9.1 or 9.01 or 9.0001. So we've approximated here. We've done an okay job, but we've approximated it. So in terms of h, it would look like this. You have your original, and then your original plus some value of h. The one thing I didn't do here is this h value should not be a full increment, and it looks even. That's not to scale. This one h value should be a sliver of a change. And you'll notice this white box here. I'll explain that in a second. If you calculate it using this x plus h value, now your y becomes this function of x, and it's not only a function of x, but it's a function of x plus h. That's the modified change. Then you have your original, and then you have your initial x, and you have your original x. Or excuse me, your modified x and your initial x. And that goes into the difference in y's on top, divided by the difference in x's. And again, these x's cancel out. So you can do it that way, but don't spend too much time on that. We're going to do it this way. So instead of h, we're going to use d of x. That's kind of more, I'll say contemporary. It's used a little bit more often. So now we have our original point, and then we have our point plus some tiny, tiny, tiny value dx. And you'll notice it's on both sides here. We have dx, and again, we have this box vacant, and I'll explain that in a second. So just to tell you, the derivative of x squared is 2x. And we're going to look at these boxes to figure out how that is. So the general rule of thumb, which you can easily memorize, but I'm trying to kind of prevent you from having to memorize it, is for an exponent, you take the exponent, you move it to the coefficient level, and then you subtract 1 from the coefficient. So we had x squared, the 2, or x to the second power. That 2 comes down, it becomes the coefficient, and you have 2x. And the exponent becomes 2 minus 1, or 1. So 2 times x to the 1, which is 2x. So why is it that? Okay, so just as we did before, you can count these boxes here. But the problem with counting them in this case is dx is not 1. It's a tiny sliver. So what we're going to do is actually calculate the area of these boxes. And the area of these boxes is simply x, or x0 in this case, x along this axis, or the base is x, and then dx is the height, right? Well, we do that for both of them. So this area is x dx, right? Well, this area is also x dx. Adding those together, we get x times dx plus x times dx, or 2x times dx. Well, if you recall, that is calculating the change in y, right? Because our output here is the area. So here the output, it was 9 times 9. The output, our y value, is 81. Here the output value became 81 times this, plus this difference that we've added. So we're calculating the change in y. But the slope is actually the change in y over the change in x. So here, the change in y equals dy over dx. Well, let's look at that. Okay, we'll get back to the corner box here in a second. So dy dx equals 2x. Well, that's our final product, but we have this. We have 2x times dx. We're solved for dy. But in order to get rid of this dx, you just divide by dx, and it becomes dx over dy over dx equals 2x. So there we've actually gotten our derivative. You've gotten your derivative simply by finding the area of the change, right? Going back, the question that should have kind of been brought to your attention along these lines is what happened to this frickin' corner box here. And when we went from 9 to 10, if we go up here, go from 9 to 10, it's colored in red. We counted it. The difference was 19. Great. But what happened to it? We all of a sudden stopped counting it. Well, the reason we stopped counting it is because the area of that box is dx times dx. And the whole purpose of using dx is to use this infinitely small number. And if we start with an infinitely small number and we then multiply it, so dx times dx, by itself, it becomes even more small. So, starting with a small number, multiplying it by another small number gives you a crazy small number, which means that when you solve for a derivative by basically calculating these areas and adding them up, you're approximating the derivative, right? But that's okay, because this calculation is so small that it would change your values by such a tiny fraction that it would be completely meaningless to even bother calculating. So, and the only way that wouldn't be meaningless is if dx is too large. And if dx is too large, well, then you didn't approximate it very well to begin with. You essentially did an average just like you did here, which is literally what we did. We took an average there. And the reason we added it is because, well, going from 9 to 10, the area of this box is 1. So we would have gotten 18, but we had to take into account that area of that box and it becomes 19. And so that was our slope between 9 and 10. Anyway, I hope this kind of brings some insight, at least unique insight, into what a derivative is. It's, from a simple standpoint, you're calculating slope. From a more complex standpoint, you're almost doing a change in, slope is a change in something, but in this case, we viewed it as a change in area.